So in this video, we're going to look at an example of doing an acylation using an anhydride. So anhydrides have this general formula. And so what they have is a leaving group that is pretty good. It's not, so the whole one side of that would be a leaving group. So that would be a leaving group. And it's a pretty good leaving group. It's not quite as good as a chloride, but when that leaves, you're going to get this resonance stabilized anion. And so that makes it a pretty good leaving group. Right? Because the more stable that conjugate base is that you kick off, the better it's going to function as a leaving group. So in practice, anhydrides can do all of the reactions that acid chlorides can do. So they react similarly to acid chlorides. And in fact, the mechanisms are identical except for the identity of that leaving group. So rather than run through every iteration, we're going to look at a common example that you might have actually done in the lab before. So we are going to look at the reaction of taking salicylic acid. So this is the structure of salicylic acid. And if we take and put an acyl group on here, if we take and convert this, so let's draw what that product would be. So there's an oxygen. So here would be the acyl group that we're adding. It's specifically going to be taking that alcohol and making it into a methyl ester. So this is now acetyl salicylic acid. Which you might know better as aspirin. And so we're not going to see, even though anhydrides react similar to acid chlorides, you can see that there are two different carbonyls on an anhydride. And in theory, either one of those carbonyls could be attacked. So it's really only useful when you're using a very small and very symmetrical anhydride. And that's what's typically used in the preparation of aspirin. So that makes this a good example to take a look at. So we see it's the CH3. So that means with the anhydride we're looking for, we want both of these to be CH3 groups. And so this is the reaction that is used to form aspirin. And as I mentioned, this is a very common laboratory experiment. So it's possible that you have done this before, possibly even in high school labs. So here is that starting salicylic acid. And if you're looking at what you're trying to form, this portion, right? So in this reaction, it's kind of the reverse of what we looked at in our acid chloride videos. So we were starting with the acid chloride and saying what we're trying to make. And so here we're starting with our nucleophile and saying what we're adding. So this portion is what's coming from the anhydride. Right? This oxygen is acting as our nucleophile. So that is the nucleophile in this reaction. Right, so if we were using an acid chloride, we would just use a little methyl carbonyl and then chlorine, right? So if we are going to use an anhydride, then we are going to use, right? So this is that structure I was just talking about, a methyl and a carbonyl. So if we're using an acid chloride, we would just throw a chlorine on there. If we're using an anhydride, then we're just going to make it into the symmetrical anhydride so that regardless of which of these carbons that alcohol attacks, you're going to get the same product. So this is acetic anhydride. Right? This is the anhydride of acetic acid. So I can start this as a nucleophile. Either one of those carbonyls can be the electrophilic carbon, and it's going to give us the exact same product. So I will show this oxygen just attacking this closest carbonyl, and we're going to swing those electrons up onto the oxygen. So completely analogous to what you saw with the acid chloride reactions. So let's continue down and draw that product. right? So just a larger nucleophile than what we've used. So this oxygen here still has its bond to hydrogen because we did not break that, but it's got a new bond to this carbon. So here's a bond to that carbon, and that carbon now has a negatively charged oxygen. It still has a bond to a methyl group, and this portion here then is going to be our leaving group. Right, because that's going to leave as an acetate, which we said up here is resonance stabilized. Okay, so now that we have this, let's make sure we have all of our charges on here. This oxygen should have a positive charge because it still has hydrogen. And let's go ahead and fill in these lone pairs of electrons. All right, so this is our tetrahedral intermediate. Right, and although we've got a more complicated nucleophile, we still have the same scenario where we've got our new tetrahedral carbon. It has a negative charge, it has a leaving group, it has where the nucleophile added, right? So this is still going to collapse and push off that good leaving group. Right, and so yes, so let's go ahead and draw this. All right, so the portion I'm drawing here is just like the more complicated nucleophile that we had. So this oxygen still has its hydrogen, and now it's got a bond to, let's follow this through. It's got a bond to a carbon. That carbon has a double bond to an oxygen, and it still has its bond to the methyl group. And what's broken off now is this acetate. So you've also broken off that acetate. Right, so we have that acetate. So that acetate can act as a base and it can remove this proton. So, and once we do that, we will have the desired acetyl salicylic acid that we are looking for. So we will remove this proton. And so what we are forming here, right, so we'll have our overall reaction going to the same place as our mechanism, right? So I'm just drawing that other portion of the nucleophile. So now this is a neutral oxygen and it has the bond to this acetyl group. So we have now made the acetyl salicylic acid, and we have also made as a byproduct acetic acid. So acetic acid is the byproduct of this reaction. And acetic acid, you recognize the smell because that is the smell of vinegar. So if you have ever opened a bottle of aspirin and noticed that it smells a bit like vinegar, now you know why. That's kind of a byproduct of how this is formed. So we have our mechanism going down here, and we have our overall reaction here, right? So that acetic acid would be a byproduct, and you'd have to remove that. So a small anhydride, like acetic anhydride, is fine, because what you would do here, this is likely to be organic soluble, this is likely to be water soluble, allowing you to separate these two by means of a liquid-liquid extraction. So we're not going to see a whole lot of reactions with anhydrides. The exception will be probably with really small symmetrical anhydrides like acetic anhydride. And so again, I want you to notice the mechanism is exactly the same as with an acid chloride. So your nucleophile attacks, your electrons come up onto the oxygen, you get your tetrahedral intermediate, that's going to collapse and kick off the leaving group. And if you've got an extra proton at that stage because your nucleophile was neutral, which this was, it was an alcohol, then you would remove that in the last step.